Hi everyone, Ross Satchell from Microchip back again. Welcome to episode 7 in our Tiny 2 bare metal series. In the previous video, episode 6, we modified our Tiny 2 Curiosity Nano so that we could measure the current consumption of the Tiny 2 by effectively disconnecting the programmer debugger. We did this by cutting the power trace and soldering in header pins. We then went through turning off unused I/O pins to prevent leakage current from adversely affecting our measurements. We then went through all of the previous projects and measured their current consumption both when the LED was on and when it was off. In this video, we will make a low power Blinky with the Tiny 2, and we'll do this with each of the real-time counter, RTC, and periodic interval timer, PIT or PIT. Then we will compare the power measurements taken so far, including those from last episode. Then just for fun, we'll find the lowest power possible for the Tiny 2 in sleep mode. So let's get started. I'm going to open the modified code from last episode for the Blinky using Timer Counter A, or TCA, and copy it as a new project and just modify it to use the RTC and PIT, since all of the other stuff will be the same. First, I will delete the init TCA function prototype and its implementation. Now we need to write an init RTC function and a init PIT function. So I will start with a function prototype and skeleton. Now let's jump to the datasheet to figure out what we need to put in these functions. I will start with init RTC. So datasheet section 23 is real-time counter. Let's start with the overview. It tells us that the RTC counts pre-scaled clock cycles in a counter register and compares the content of that counter register against a compare register and a period register. It can generate interrupts and events on compare, match, or overflow. If using the overflow interrupt, an overflow of the RTC will reset the counter to 0. The RTC peripheral typically runs continuously, including in low-power sleep modes, which is ideal for this application. Also, it can wake up the device from sleep modes and interrupt the device at regular intervals. This is exactly what we want. The reference clock is typically a 32.768 kHz external crystal, but we can also use the internal 32.768 kHz ultra-low power oscillator, or even that same ultra-low power oscillator divided by 32, giving 1024 counts per second. The RTC has a prescaler giving a wide range of resolutions and timeouts. Assuming the user is using the 32.768 kHz clock source, the maximum resolution is 30.5 microseconds, and the maximum timeout can be up to 2 seconds. If the user opts for a resolution of 1 second, the maximum timeout is more than 18 hours. Then for the PIT, we can see that it uses the same clock source as the RTC function and can generate an interrupt or event on every nth clock period. For interrupts, the user can select a base 2 value, so 4, 8, 16, and so on, up to 32,768. Taking a quick look at the block diagram, we can see the clock sources. So there's an external clock, an external 32.768 kHz crystal, and the internal 32.768 kHz oscillator. Note that the internal oscillator has a divide by 32 option, which gives us a clock of 1.024 kHz. All of these feed into the clock selection multiplexer. A 15-bit prescaler is available, which controls the RTC count and feeds the periodic interval timer, or PIT. Then the count is compared to period overflow and compare registers for setting interrupt flags. Then there's an important note for using other peripherals, that the peripheral clock needs to be at least 4 times faster than the RTC clock, regardless of the prescaler setting. Now moving on to the functional description. It explains that the RTC offers 2 timing functions, that being the real-time counter, RTC, and the periodic interval timer, PIT. So this first section we're going to cover the RTC. Firstly, the initialization of the RTC. So before enabling the RTC peripheral and its associated interrupts and events, the source clock must be configured to use the RTC. So to configure the RTC clock, step 1, configure the required oscillator in the clock control peripheral. Step 2, write the clock select bit field in the RTC clock select register, and note that this RTC clock configuration is used by both the RTC and PIT functionalities. Then we need to configure the RTC for operation. So step 1 is set the compare value in the RTC compare register and or the overflow value in the RTC period register. Step 2, enable the desired interrupts by writing to the respective interrupt enable bits, so that's compare and overflow, in the RTC int control register. Step 3, configure the RTC internal prescaler by writing to the prescaler bit field in the RTC control A register. Step 4, enable the RTC by writing a 1 to the RTC peripheral enable in the RTC control A register. Now while we're here, let's also take a look at the PIT functional description. So datasheet section 23.5 is the PIT functional description. And under initialization, it says we need to. Step 1 is configure the RTC clock, which is much the same as we looked at just earlier. Step 2, next we need to enable the interrupt for the PIT in the PIT int control register. Step 3, select the period for the interrupt in the PIT control A register. And step 4, enable the PIT in the PIT control A register. So section 23.10 talks about synchronization, and it tells us that both the RTC and PIT are asynchronous, operating from a different clock source to the peripheral clock. So for control and count register updates, it will take some RTC clock cycles for an update of those registers to take effect. For the RTC, there's a sync busy flag in the RTC status register, and for the PIT, that flag is in the RTC.PIT status register, and we should check those flags before writing to the relevant registers. Okay, so let's jump back to MPLAB X to implement the RTC initialization. So step 1 was setting the RTC clock. Let's go into our main clock control function. So previously we had the 20 MHz oscillator, but in this video we want the 32.768 kHz internal oscillator. Now as you can see here, the macro for the 20 MHz oscillator starts with clock control _ clock select. So we can simply go to the header file and search for that. It takes us to the enum containing all of the group configurations for the clock selection. Note that there's 2 group configurations for 32 kHz. There's the ultra-low power internal oscillator, and then there's the external crystal oscillator. We want the ultra-low power internal oscillator. I'm just going to copy that macro and return to the main.c file. So for main clock control A, we just replace the macro for 20 MHz oscillator with the macro for the internal 32 kHz oscillator. There's several ways we could do the main clock and RTC clock. We could use a prescaler in the main clock and adjust our RTC period accordingly. Or we could turn the main clock prescaler off and directly count the full number of clock cycles in the RTC. I'm going to do the second one, that is, turn off the main clock prescaler, and then for the RTC clock, I will use the internal 32 kHz clock and then just count 1 second, which with a 32.768 kHz clock means 32,768 clock cycles. So to do that, I need to write to main clock control B. Let's quickly jump to the datasheet. So in section 11, clock control, I'll go straight to the register summary. We have a bit field for the prescaler division. Notice that the smallest prescaler is 2. So if we want to pass the clock through without division, we need to disable the prescaler. Bit 0 is the prescaler enable, and we can see when this bit is written to 0, the main clock passes through undivided regardless of the value of the prescaler. That's exactly what we want. Very importantly, note that the PEN bit, upon reset, defaults to a 1. Jumping back to MPLAB X, let's go to the header file again to get the relevant macro. So let's search for the module, which is clock control, then underscore, then the bit name, which is PEN. There it is. Now remember that we want to write a 0 to that bit, but the PEN macro is a 1. So we could directly write a 0 to that bit in main clock control B, but I want to use macros to make it human readable. So to use that macro, which writes a 1 with the PEN bit or prescaler enable bit in the main clock control B register, which is also a 1, we need to use the NAND operator. If it's been a while since you've done digital logic, let's do a quick refresher. Here's the logic gate and truth table for a NAND gate. So when both inputs are 1, the output is 0. In all other cases, the output is 1. So our prescaler defaults to a 1 upon reset, and the PEN macro is also a 1. So when we NAND them together, it will clear, that is, write a 0 to our register bit of interest. Let's jump to TB3262, getting started with writing C code for AVR microcontrollers, link in the description below, to see how to implement that in code. So section 3 is writing bare metal C code for AVRs, then just under that is section 3.1, set, clear, and read register bits. Then under that there are two methods, one using bit masks and the other using bit positions. I'm going to use bit masks, but you could also use bit positions. We can see that there's a note that to clear a bit from a register, we use the binary AND with the negated bit mask. Now jumping back to MPLAB X, in the protected write for main clock control B, we can bitwise AND the current contents of main clock control B with the negated bit mask for the prescaler. What I mean by that is that we don't need to use the equals operator here because of the way that the protected write works. We covered that in earlier episodes, but if you wanted to revisit that, you can also go to section 3.5, Writing to Configuration Change Protection, CCP registers, for details. That's it for the main clock control function. Now we need to configure the RTC clock source. Now I'm just going to implement the steps outlined earlier. Write the clock select bit field in the RTC.clockselect register. So let's go to the header file to search for RTC_clockselect. I'm looking for the enum with the group configurations in it. The top one with the internal 32 kHz oscillator is the one that I want, so I'll just copy that. Now back to the main.c file. I'm going to use the overflow, so I need to write to the RTC period register, and as I mentioned earlier, I want it to count to 32,768 since we're using the 32.768 kHz oscillator. That way I'll get an overflow every 1 second. This is where we need to check the synchronization flags that we covered earlier. Let's quickly jump to the RTC register summary in the RTC status register. So there's several synchronization flags. Compare, which we're not using, then period sync. We will need this to write to the RTC period. Then countersync, which we don't need to worry about, then control async, which we will need for the RTC configuration. So back in MPLAB X, inside the RTC init function, I can do a while loop in which I check the RTC status register, bitwise ANDed with the RTC period busy bit mask. So when the RTC period is being synchronized, this will resolve to 1 and it will stay inside the while loop. Then when the RTC period busy flag returns to 0, we will then break out of the while loop. Now we can write to the period register, and the value was 32,768. So the next step in the RTC configuration was to enable the necessary interrupts in the int control register. There's only 2 bits in use. One is the compare match enable, which we're not using in this example. Then there's overflow interrupt enable, which we need to set to 1. So back in MPLAB X, RTC.intControl equals RTC_OVF for overflow _bitmask. Next two steps use the Control A register, so let's quickly check it in the datasheet. So there's Run Standby, which we will need to write a 1 to enable running in standby sleep mode. Then the prescaler, we want no prescaling, which is the macro div1. We don't need to worry about frequency correction in this example. Finally, there's the RTC peripheral enable, and we'll need to write a 1 to that. Back in MPLAB-X, so we need to check in the Control A synchronization register to make sure it's not busy when we write to it. So just like before, it's a while loop, but this time we bitwise and the RTC Control A register with the RTC underscore Control A busy bit mask. While that expression evaluates to 1, meaning it's busy, we stay in the loop. Then when that expression evaluates to 0, meaning it's no longer busy, we can write to the Control A register. So we want Run Standby ORed with the prescaler of 1 group configuration, then that is ORed with the RTC enable bit mask. That's it for the RTC initialization. Now let's do the PIT initialization. In the init PIT function we created earlier, I will set up the clock. I want to use the 1 kHz clock. This is very similar as we did for the RTC. Now we set up the interrupt in the PIT int control register. The only bit available is the periodic interrupt, and we can use the bit mask for that. RTC underscore PI underscore bit mask. Now we need to select the period, but remember, we need to take care of the synchronization. Let's look at the PIT status register. There's only one bit there for control busy. Just like for the RTC, it's a while loop, and we bitwise AND the PIT status register and the RTC control busy bit mask. As long as it's busy, that while loop will resolve to true, or 1, and it will stay in the loop. Once it's no longer busy, it will break out of the while loop, and we can then select the period and enable the timer. Since both of those use the Control A register, we can just do them on the same line. For the period, it's the module RTC, then the bit field period, then the setting CYC1024, then GC for group configuration. Then bitwise OR that with the PIT enable, so it's the module RTC, then the PIT enable bit, and then BM for bit mask. Now we need to set up the relevant interrupts. The process is very similar to what we did in episode 5, where we were using TCA0 interrupts. So jumping to the datasheet, section 8.2, interrupt vector mapping, and we can see there's an RTC overflow interrupt vector, and there's also an RTC PIT interrupt vector. Back in MPLAB-X, we can just modify the TCA0 interrupt service routine that was used in a previous episode. So first we need to put in the interrupt vector name, which was RTC underscore count, and then it's a vector. While I'm here, I'm going to add the skeleton for the PIT ISR too. I'll just copy the RTC ISR and change the vector name to RTC PIT. In the TCA0 ISR, we toggled the LED and reset the interrupt overflow flag. In the RTC ISR, we will also toggle the LED, but this time we will reset the RTC interrupt flag. Then in the PIT ISR, we will do the same, except of course we will be resetting the PIT interrupt flag. So let's jump back to the datasheet, RTC register summary. So we've already done the Control A, status, and int control registers. The next register is interrupt flags. There's a compare match flag, but we're not using compare. Then there's an overflow interrupt flag, and it tells us that the overflow flag is set when the RTC count register reaches the value in the RTC period register. To clear the flag, we just need to write a 1 to it. Then for the PIT interrupt flag, we will use the PIT int flags register, and to clear that flag, we will just write a 1 to the PI bit. Back in MPLAB-X and the RTC ISR, so after toggling the LED, we'll write to the int flags register using the OR equals operator, and then the RTC overflow bit mask to clear the flag. Then in the PIT ISR, we will write to the PIT int flags register with the same process. Finally, in the init sleep function that we used in episode 5, we have sleep mode idle. Recall that we saw that the datasheet indicated that the RTC can operate in standby sleep mode, and we have enabled the run standby bit for the RTC. I'm going to add a couple of lines of code enabling standby sleep mode and then power down sleep mode for the PIT so that we can comment out one or the other to select different sleep modes. Let's quickly jump to the datasheet, section 12 sleep controller, and go to the register summary. We can see the macros for the S mode bit field. So let's add each of them and just comment out the ones we're not using. So now in the main function, we'll first call the init RTC function with idle sleep mode and measure the current. Then we will switch to standby sleep mode and measure the current again. Then we will comment out the init RTC function and instead call the init PIT function, and then we will use power down sleep mode and measure the current. Finally, we will disable the PIT and enter power down sleep mode and measure the current. Then we can compare all of the current consumption so far for Blinky's using TCA, RTC, and the PIT. And then we can also do the lowest possible power operation. Now I'm going to switch the Microchip power debugger here to measure the current because it runs in Data Visualizer, and I can set up cursors to get the total charge used for a time period and then just use that to calculate a battery life. There's already plenty of content available on setting up and using the power debugger, so I won't go into those details here. So recall from episode 6, we did low power measurements of the previous projects. So for TCA in idle mode, when the LED was on, we had 1.55 milliamps, and when the LED was off, we were using half a milliamp. Then with TCA in standby mode, we found we were using about the same amount of current. Then in this episode, with the real-time counter, or RTC, in idle mode, we were measuring about 0.95 milliamps when the LED was on, and about 2.8 microamps when the LED was off. With the RTC in standby mode, we measured 0.95 milliamps when the LED was on, and about 2.7 microamps when the LED was off. Then with the PIT in power down mode, we were measuring about 0.95 milliamps when the LED was on, and about 2.4 microamps when the LED was off. Then finally, with all of the peripherals disabled in power down mode, we were measuring about 1/4 of a microamp, that is about 250 nanoamps, with the LED off. So by switching from using TCA to the RTC or PIT, we reduced our current consumption from half a milliamp to 2.4 microamps. So that's using about 200 times less current. Let's compare those values to the datasheet values, section 33 electrical characteristics, then under that, section 33.5 power consumption. Idle sleep mode with the 32 kHz internal oscillator at 3 volts shows a current consumption of about 2.4 microamps, and we are seeing slightly higher than that at 2.8 microamps, and that could be attributed to the leakage current of the I/O pin, as well as potentially leakage current of the debug pins, since we're using a Curiosity Nano. Then standby sleep mode, we were seeing about 2.7 microamps, and the datasheet shows a maximum of 2 microamps at 25 degrees. So again, the most likely culprit here is leakage from the I/O pin, and also possibly from the debug pin, since we're using the Curiosity Nano again. Then the RTC does not operate in power down mode, however the PIT does. And we were seeing about 2.4 microamps with the LED off. The datasheet says in power down mode with all peripherals stopped, we should be measuring about 0.1 microamp with a maximum of 1.5 microamp. And we found that when we turned off all of our peripherals, we were measuring around 250 nanoamps in power down sleep mode, which is well within that maximum spec of 1.5 microamps. For the lowest powered Blinky, we're measuring over the course of 1 minute about 7.7 microamp hours. If we were to power this using a CR2032 battery that has a capacity of 235 milliamp hours, we can easily calculate the lifetime of the battery as follows. Take our 7.7 microamp hours, multiply by 60 to get 1 hour, then multiply by 24 to get 1 day. Then divide that by the battery capacity to get the lifetime in days, and we get 21.1 days, keeping in mind that the vast majority of that current consumption is the LED. So let's also do the measurement and calculation for power down mode with all of the peripherals stopped. And we can see over the course of 1 minute, we consumed 3.21 nanoamp hours. If we run our calculation again, we get 139 years. So the battery's shelf life would expire many decades before we use the full capacity of the battery. Of course, if we were to look at the discharge curve of a CR2032 battery, it would be a bit less than that as the battery voltage drops towards the end of its life. But it gives us a decent idea of just how good the low power modes are on the Tiny 2. So as you may recall, I've mentioned previously that this series will culminate in a small project using the following peripherals: USART, ADC, SPI, and sleep control. So to reach that end goal, in the next episode, we're going to set up a USART and write to the terminal.